Chapter 1 Chemical Kinetics Introduction. Chemical kinetics is the branch of chemistry which deals with the rate of chemical reactions, the factors which affect the reaction rates, and the mechanism by which these reactions occur. In other words, chemical kinetics tell us how fast a particular reaction takes place and what mechanism it follows. Also, it tells us how the reaction rate is dependent on variables like temperature, pressure, and the concentration of the reacting species, etc. The chemical reaction can be classified into following categories on the basis of their speeds. First, instantaneous reactions, which occur at very fast speed. These reactions occur as soon as reactants are mixed and is practically not possible to measure the speeds of such reactions. By ordinary methods, such reactions include several ionic reactions, neutralization reactions of acid and bases, etc. Examples are AgNO3 plus NaCl give AgCl plus NaNO3. NaOH plus 4HCl gives NaCl plus H2O. Second is extremely slow reactions, which produced which proceed at very low speed. For example, rusting of iron, combination of hydrogen and oxygen at ordinary temperature, etc. These reactions occur at such low speed that it is not possible to determine the rate of these reactions. Next is reactions which proceed at measurable speed. There are chemical reactions which proceed at moderate speed, which can be easily measured. Some examples of such type of reactions are hydrolysis of ester. Next is inversion of cane sugar, decomposition of HI. Different chemical reactions proceed at different rates. An obvious reason for this is that a chemical reaction involves breaking of bonds in the reactants and formation of new bonds in the products. The energy required for bond breaking and energy evolved for bond formation is different for different reactions. That is why different reactions proceed at different rates. The instantaneous reactions involve just combination of ions that are already present in solution. Hence, these reactions occur at very fast rate. The reaction which measurable rate are the focus of attention in chemical kinetics. Chemical kinetics is concerned with the following aspects: the rate of reaction and the rate laws. What is the effect of temperature, pressure, concentration, and catalyst on the rate reaction? What is the mechanism or the sequence of steps by which the reaction occurs? Rate of reaction. The rate of chemical reactions or the reaction velocity may be defined as the change in concentration of any of the reactant or the product per unit time. For example, consider a simple reaction. Rate of reaction equals to decrease in concentration of A divided by time taken equals to increase in concentration of B divided by time taken. Units of rate of reaction. Rate of reaction has unit of concentration divided by time. The concentration is usually expressed in moles per liter. For gaseous reactants, instead of concentration, we take pressure in atmosphere, and time may be expressed in seconds, minutes, or hours. Therefore, the units of reaction rate are as follows: moles per liter per second, or moles dm cube second, or moles per liter per second, moles per liter per minute, or moles per liter per minute, or moles per liter per hour. For gaseous reactants or products, the concentration term is expressed in terms of partial pressure. Therefore, the units of rate of reaction will be atmosphere second inverse. The molar concentration of reactants and products keep on changing with time. Therefore, the rate of reaction is not uniform throughout but keeps on varying. Therefore, it is more appropriate to express the rate of reaction at a particular instant of time. Such a reaction rate is called instantaneous rate of reaction and is defined as the change in concentration of any one of the reactant or products as a particular instant of time, expressing the instantaneous rate of reaction. According to law of mass action, The rate of reaction depends upon the molar concentration of the reactants. As the concentration of reactants changes with time, so the rate of reaction also changes with time. Therefore, it is more appropriate to express the rate of reaction at a particular instant of time. To express the rate of reaction, a small interval of time dt is taken and is assumed that the rate of reaction remains constant in the interval of time. If dx is the small change in concentration of any of reactant or the product, then the rate of reaction is expressed as rate of reaction equal to dx by dt. In case of reactants, concentration decreases with time, therefore a negative sign is put before dx by dt. On the other hand, the concentration of product increases with time, hence a positive sign is written before dx by dt. Consider the following reaction. A plus B convert into L plus M. The rate of such a reaction is expressed in terms of fall in concentration of reactant or increase in concentration of product. Thus, the rate of reaction based on the rate of change of concentration of each species is written as rate of reaction equals to dx by dt minus d of A divided by dt equals to minus d of B divided by dt equals to plus dl by dt equals to plus dm by dt. It may be implied that the rate of reaction is always positive. The negative sign in above expression indicates the fall in concentration of the reactant, where the positive sign in the expression indicates the increase in concentration of the product. With the passage of time, here d of A and change in concentration of B represent the small decrease in concentration of reactant A and B, and change in concentration of L and M represent the small increase in concentration of products L and M. For a general reaction, A of A plus B of B equals to L plus M. The rate of reaction is written as, where A, B, L, M, N are stoichiometric coefficients measuring the rate of reaction. The rate of reaction can be measured by plotting a graph between the concentration of any of reactants as a function of time. The concentration of any of the reactant or the product is measured at different interval of time. For this, it is necessary that all other variables except concentration which may affect the reaction rate remain constant. Usually a reaction is carried out and small amount of reaction mixture is withdrawn at small intervals of time. This reaction mixture is cooled at a temperature below 0 degree Celsius by keeping it in freezing mixture. By doing so, the reaction is arrested. No further reaction takes place. No, the concentration of any of the reactant or product is determined by suitable method, usually titration etc. After determining the concentration of reactant or a product, the concentration time curve is plotted as shown in figure 1. Figure 1 is graphical method for measuring rate of reaction. It is not always required to stop the reaction for measuring the concentration of any species at various time intervals. The same information can be obtained by nothing the changes in observable properties like change in color, change in pH, volume, pressure, optical rotation with time. Accordingly, the graphs are plotted to calculate the rate of reaction. All the method will be taken up we proceed in the chapter. However, we change in concentration of a reactant or a product is measured with time, then the rate of reaction is determined as follows. Curve in figure first A and figure first B show the variation of concentration of reactant with time, and figure first C the change in concentration of product with time. In such type of concentration time curves, the reaction rate is determined by two methods. First is the rate of reaction at any instant of time can be determined by drawing tangent to the concentration time curve at that particular instant. The slope of tangent then gives the required rate of reaction at any instant. A small change in concentration dx in a small time interval dt is noted directly from the concentration time curve, assuming that the rate of reaction remains constant during this small interval of time. The quantity dx by dt gives the required rate. Figure first C shows the increase in the concentration of product with time. The rate of reaction can be determined by drawing tangent to the curve of the given instant of time or by reading directly the values of dx and dt from the curve. Factors affecting the rate of reaction. The rate of reaction is influenced by following factors. First, nature of reactant, concentration of reactant, temperature of the system, presence of catalyst, exposure of radiation, nature of solvent. For a reaction in heterogeneous system in which a reactant is in solid state, and the surface area of reactant also become an important factor which affects the rate of reaction. By studying these factors which affect the reaction rates, it becomes possible to control the rate of reaction. Nature of reactants. Substances differ in activity and hence in the rate at which they react with other substances. Active metals react slowly, hence the rate of reactions are affected by the nature of reactants. Following examples clearly show this effect. Oxidation of nitric acid and carbon monoxide in air. Above two reactions seems identical. There are same number of moles of reactants and the products in both the cases, and both are oxidation reactions, but they differ in their rates. The reason is that nature of reactants. NO and CO must be different, hence there is difference in the rates of these reactions. Combination of chlorine and bromine with hydrogen, both these reactions are similar as shown ahead. Under similar conditions, the first reaction is fast while the second one is slow. This difference in rates of two reactions can be attributed to the nature of halogen. So, rate of reaction are influenced by the nature of reactants. A chemical reaction involves the breaking of old bond and formation of new bonds. The reactivity of a substance is therefore related to the assay with which the specific bonds are broken, and the number of such bonds involved as the amount of energy required to break the bonds is different in different reactants. Hence, the rate of reaction also vary with the nature of reactants. Concentration of reactant. It has been observed that the rate of chemical reaction keeps on decreasing with time. The concentration of reactant is maximum at the start of reaction, and therefore the rate of change of concentration is also maximum. As the concentration of reactant decreases, it brings about the corresponding decreases in the rate of reactions. Also clearly indicates that the rate of reaction is already proportional to the concentration of the reactant. The change in the concentration of reactant and therefore the rate of reaction with time is shown in figure 2. From the above figure, it is clear that the start of the reaction, the rate of reaction is large and it decreases with the passage of time. Therefore, to increase the rate of reaction, we should increase the concentration of one or all the reactants in a gas phase reaction. The increase in pressure of the reactant gases increases the rate of reaction. With increases in pressure, the number of molecules per unit volume increases and therefore rate of reaction increases. The effect of concentration of reactant on the reaction rate may be explained in terms of collision theory. According to collision theory, the rate of reaction depends upon the number of collisions per second between the reactant molecule. By increasing the concentration of one or all the reactants, the number of collisions increases and it leads to an increase in the rate of reaction. Temperature. It depends upon the temperature of system. In general, an increase in temperature increases the rate of almost all chemical reactions. Temperature coefficient equals to rate constant T plus 10 degrees Celsius divided by rate constant T degrees Celsius, where K1, KT and KT plus 10 are the specific rate constant at T degrees Celsius and T plus 10 degrees Celsius respectively. For example, the temperature coefficient for the saponification reaction of ethyl acetate with sodium hydroxide is 1.75, where the value of temperature coefficient for reaction between methyl iodide and sodium ethoxide in solution is approximately 2.9. Explanation of effect of temperature on rate of reaction. The increase in reaction rate with increase in temperature is explained on the basis of collision theory. According to collision theory, the chemical reaction occurs as a result of collision between the reacting molecules. However, all collisions do not result in chemical reaction. Only effective collision between the reactant molecule result in formation of products. According to collision theory, only a small fraction of collision is effective in bringing about the chemical reaction, and the rest of the collisions are ineffective. For an effective collision, the colliding molecule must have more than or equal to certain minimum amount of energy called threshold energy. Concept of activation energy barrier. Familiar reactions such as burning of coal in air, combination of hydrogen and oxygen gases do not occur unless some extra energy in one form or the other is supplied to them. This is because in such reactions the reactant molecules do not possess energy equal to the greater than threshold energy under normal conditions, so there is no reaction. Thus some extra energy has to be supplied to the reactants to bring their energy equal to threshold energy, and then the reaction starts. The excess energy which must be supplied to the reactants so that their energy becomes equal to threshold energy is called activation energy EA. It is equal to the difference between the threshold energy for the reaction and the energy possessed by all the reacting molecules. That is activation energy equal to threshold energy minus energy possessed by the reacting molecules. This is shown graphically in figure 4. The activated complex has a very short lifespan and splits into the products. In case of oxidation of NO, the activation energy is small and thus only a small increase in energy enables reacting species to cross the energy barrier to form NO2. Therefore, the reaction is also so large amount of energy is required by reactants to cross the activation barrier. Hence, the reaction is slow at room temperature. Thus, we conclude that if activation energy is low, the reaction is fast. If the activation energy is high, the reaction will be slow. Presence of catalyst. A catalyst is a substance which increases the rate of chemical reaction and can be recovered chemically unchanged at the end of the reaction. For example, manganese dioxide speeds up the thermal decomposition of potassium chlorate. Manganese dioxide acts as a catalyst in the reaction and can be recovered unchanged at the end of the reaction. Following points must be noted about the function of catalyst. A catalyst does not change del E of the reaction. This is clear from the figure 5 that the addition of catalyst does not change the energy of the reactants and the products, so that del E remains the same. Although the catalyst speeds up the reaction, but it does not affect the position of equilibrium in case of reversible reactions. This is because the activation energy for the forward reaction and backward reaction is reduced to the same extent. As a result, the increase in the rate of the forward and backward reaction is same, and hence the position of equilibrium remains unaffected. However, catalyst increases both the rate, hence the equilibrium is attained earlier. Exposure to radiation. In some cases, the rate of reaction is considerably increased by the use of certain radiation. The photon of these radiations possess sufficient energy to break certain bonds in reactants. For example, reaction of hydrogen and chlorine takes place very slowly in the absence of light. However, in presence of light, the reaction takes place very rapidly. Nature of solvent. Nature of solvent also affects the rate of reaction. These effects can be studied under the following properties of solvent: magnitude of dielectric constant of the solvent, polarity of solvent, effect of solvation. First is magnitude of dielectric constant of the solvent. In case of ionic reaction in solution, the interionic forces are largely affected by the dielectric constant of the solvent. Therefore, the rate of reaction is found to vary with the dielectric constant of solvent according to the following equation, where D is the dielectric constant of the solvent and A and B are the constant of two ions in solution. According to the above equation, the logarithm of the rate constant should vary linearly with reciprocal of dielectric constant of the solvent at a particular temperature. Therefore, a plot of ln k with 1 by d should give a straight line. Next is polarity of the solvent. The reaction between polar reactants, the rate of reaction is greatly affected by the polarity of the solvent. It has been observed that a polar solvent increases the rate of reaction in which the product formed is more polar than reactants and decreases the reaction rate if a product formed is less polar than the reactants. For example, the formation of a quaternary ammonium salt formed by reaction between triethyl amine and ethyl iodide is favored by increasing polarity of solvent as shown in table 1. This is because the product is more polar than the either of the reactants. On the other hand, the reaction between acetic anhydride and ethyl alcohol giving rise to ethyl acetate is not favored by increasing polarity of the solvent. The region being the product formed here is less polar than the reactants. So the solvents which favor the formation of quaternary ammonium salts and tend to slow down the esterification reaction in which the product are of lesser polarity than the reactants. The order of polarity of solvents in table 1 is nitrobenzene greater than benzene and benzene greater than hexane. If the reactants and the product do not differ much in polarity, then the effect of polarity of solvent is insignificant on the rate of reaction. For example, in decomposition of nitrogen pentoxide to form nitrogen trioxide and oxygen, the reaction rate is almost unaffected by the polarity of the solvent because the reactant and product rate products are of almost same polarity. This fact is clear from the data given in table 2. Influence of solvation. The rate of reaction is largely affected by the degree of solvation of the reactant and the activated complex. The solvation of reactant or activated complex lowers their potential energy by an amount equal to solvation energy. Three different cases of solvation are shown in figure 7. Case 1. The reactants are appreciably solvated but the activated complex is not. In the situation, the potential energy of reactant is lower due to solvation. In figure 7a, as a result, the energy of activation for the reaction increases and the rate of reaction decreases. Case 2. The activated complex is solvated but the reaction are not. In the case of potential energy of activated complex decreases due to solvation, figure 7b. The energy of activation of the reaction decreases, consequently, the rate of reaction increases. Case 3. Both the reactants and the activated complex are solvated. In such a situation, the potential energy of reactants and activated complex decreases due to the solvation in figure 7c. The net result in increases in the activation energy of reaction and hence the reaction will take place slowly than in a solvent in which the reactants and activated complex are not solvated. Concentration depends of reaction rate. Law of mass action. When a chemical reaction proceeds, the reactant got converted into products. As a result, the concentration of reactants decreases while rate of product increases. The quantitative relationship between the rate of reaction and molar concentration of the reacting substances is known as law of mass action. According to this law, at a given temperature, the rate of chemical reaction is directly proportional to the product of the molar concentration of reactant. Consider a simple reaction. According to the law of mass action, rate of reaction may be written as rate equals to K A concentration term A and B has concentration term B, where A and B are the molar concentration of reactants. K is constant of proportionally and is called rate constant or velocity constant. Now, if concentration of each of the reactant is unity, A equals to B equals to 1 mole per liter, then substituting these values in above expression, we get rate of reaction equals to K. Thus, the rate constant of a reaction at a given temperature may be defined as the rate of reaction when the concentration of each of the reactant is unity. Hence, the rate constant is called specific reaction rate. Rate law expression. The actual dependence of rate on concentration of reactant or product is measured experimentally. For example, in reaction A plus B gives products. The dependence of rate of reaction on concentration is found to be rate equals to K. A has concentration term alpha and B has concentration term beta, where alpha and beta are experimentally determined powers of concentration of reactants A and B, and respectively on which the reaction rate depends. The power of alpha and beta may or may not be equal to the coefficient of A and B in the reaction. The expression 2 is the rate law or rate equation. Rate law differs from the rate law of mass action. The rate law gives experimentally observed dependence of rate on the concentration of reactants. The power of concentration of reactants in rate law expression may or may not be same as the coefficient of concentration in the balanced chemical equation. In above general equation, according to law of mass action, and the rate law expression is order of reaction. Order of reaction is defined as the sum of the power of which the concentration term are raised in the rate law equation to express the observed rate of the reaction. Thus, if the rate of reaction is given by the rate law as rate equals to minus dx by dt, then the order of the reaction n is n equals to p plus q. If n equals to 1, the reaction is said to be first order reaction. If n equals to 2, the reaction is said to be second order, and so on. Some common examples of reactions of different orders are given below. Zero order reactions. A number of reactions are known in which the rate of reaction is independent of the concentration of the reactants. For example, the decomposition of ammonia at the surface of metals like platinum 2NH3 in the presence of platinum to give N2 plus 3H2. The rate of reaction is independent of the concentration of ammonia. Rate equals to K NH3 concentration 0, rate equals to K, order equals to 0. Thus a reaction is said to be zero order if its rate is independent of the concentration of reactant. In such reaction, the rate of reaction remains constant throughout. The amount of substance reacted to proportional to the time. Zero order reaction are relatively uncommon. Many photochemical reaction and heterogeneous reaction have been found to be a zero order. Photochemical reactions. The reactions which take place in the presence of light are called photochemical reactions. Many photochemical reactions, example formation of HCl from H2 and Cl2, are example of zero order reaction. The kinetics of the combination reaction of H2 and Cl2 in the presence of light can be studied in the laboratory by simple experiment. A test tube filled with a mixture of H2 and Cl2 gas is inverted in a trough containing water. The setup is exposed to sunlight and the photochemical reaction takes place. The HCl formed is soluble in water. As a result, the level of the water rises in the test tube. It is found that after some time the amount of H2 and Cl2 decreases, but their concentration remains unchanged. This proves that photochemical reactions between H2 and Cl2 is zero order reaction. Heterogeneous reactions. Zero order reactions are found in heterogeneous system. A heterogeneous system, the reactants, products, and the catalyst are present in different phases. The well-known examples of heterogeneous reaction with zero order are: first is decomposition of hydrogen iodide on the surface of gold, and second is decomposition of ammonia on the surface of metals like platinum, molybdenum, or tungsten at high temperatures. In such reactions, the reactant is absorbed on the surface of the catalyst, where it is converted into the product. At low concentration, the reaction is first order, but when the surface of the catalyst becomes fully covered with the reactants, the reaction becomes zero order. On increasing the concentration of reactant, the reaction rate does not change. In other words, the rate becomes independent of the concentration and therefore becomes zero order reaction. For example, the decomposition of NH3 on the surface of finely divided platinum in first order when the pressure of NH3 in the system is low. However, at higher pressure, When the surface of the catalyst becomes fully covered with the layer of NH3 molecules, the reaction becomes zero order. Some enzymes catalyst reaction are also zero order reaction. Integrated rate expressions. We have learned that the instantaneous rate of reaction is given by differential rate law equation. For example, for a general reaction, the differential rate law equation is dx by dt equals to k. A has concentration term A and B has B. The differential form of rate law is transferred to integrated form of rate equation. The integrated rate equation for different order reaction can be derived as given below. Zero order reaction. In a zero order reaction, the rate is independent of the concentration of reactants. Consider a general zero order reaction. A gives products. Let A be the concentration of reactant and K is the rate constant for a zero order reaction. Since the rate of reaction is independent of concentration of reactant A, thus rate equals to K. This is differential rate equation. Rearranging above the equation, we get minus d of A equals to K dt. Integrated above the equation, we get minus of A equals to kt plus I, where I is the constant of integration. The value of I can be calculated from initial concentration. Let the initial concentration of A be at T0. Above equation becomes I equals to minus A naught. Substituting the value of I in equation 2, we get K equals to 1 by T A naught minus A. This is the integrated rate expression for zero order reaction. The rate constant K can be calculated if we know the concentration of A at any time and the initial concentration of A naught. Alternatively, the rate constant K can be calculated as follows. Let the initial concentration of A be A moles per liter and let X of reactants convert into product in time t. Then concentration of A left after time t be A minus X moles per liter. This is general equation for zero order reaction. X equals to K T. It shows that a zero order reaction, the amount of substance reacted is proportional to the time. Important characteristics of zero order reaction. First, the integrated rate law equation for zero order reactions are. It can be seen from equation 2 that we plot a graph between A against T. We get a straight line with slope minus k and intercept equals to A naught in figure 9a. The differential rate equation for zero order reaction is rate equals to k. It is clear from the equation that rate of zero order reaction is independent of concentration of reactants. Therefore, a plot of rate of reaction versus concentration of reactants will be a straight line parallel to concentration axis. Half-life for zero order reactions. Half-life T half of a reaction is the time required for the concentration of reactant to decrease to half of its initial concentration. T half equals to A naught by 2K. Thus, the half-life for a zero-order reaction is directly proportional to the initial concentration of the reactant. That means if the initial concentration of reactant is made double, the time required for reaction to be half completed is also doubled and so on. Units of rate constant K. The rate equation for zero order is and the unit is moles per liter per time. Kinetics of first order reaction. A reaction is said to be first order if the rate depends upon one's concentration variable only. Consider a first order reaction. If the initial concentration of A is A moles per liter and let X moles of the reactant get changed into products in unit time t. Then the concentration of A after time t is A minus X moles per liter. Then according to law of mass action, the rate of reaction inverse directly proportional to A dx by dt directly proportional to A minus X equals to K into A minus X, where K is the rate constant or specific reaction rate for first order reaction. Equation first is the differential rate equation, rearranging above equation we get dx by a minus x equals to k dt. Integrated this equation we can write minus ln a minus x equal to kt plus I, where I is the constant of integration at the start of reaction, that is at 0 t is 0 and x is 0, because the reactant has not reacted. Substituting these values in equation 2 we get minus ln a equals to I. Substituting the value of I in equation 2 we have k equals to 2.303 t log a divided by a minus x. Equation 4 may also be written in an alternate form as follows. The initial concentration of A is C naught at t equals to 0 and time t. The concentration of A is Ct. Then putting A equals to C naught and A minus x equals to C of t. In equation 4 we get K equals to 2.303 divided by t log C naught by Ct. Similarly, equation 3 may be then be written as kt equals to ln c naught divided by ct. Equation 6 may also be written in exponential form as ln c naught by ct equals to kt, or ln ct divided by c naught equals to minus kt, taking until log on both sides. Ct divided by c naught equals to e की power minus kt, ct equals to c naught e की power minus kt. This is very useful form of integrated first order reaction equation, as it directly gives the concentration of reacting species at any time Ct if the initial concentration is C naught and the rate constant K are known. Important characteristics of first order reactions. By substitution method, all the reactions of first order obey the following equations. So, starting with a known concentration A or C naught, the concentration of the reactant A minus X or Ct is noted at different intervals of time. The value of concentration of A minus X or Ct at different intervals or substituted in the above equation. If the value of K comes out to be constant, then the reaction is of first order. By graphical method, equation 5 may be written as kt divided by 2.303 equals to log C naught by Ct, or log Ct equals to minus k divided by 2.303 t plus log C naught. This equation is comparable to equation of a straight line y equals to mx plus c, when a graph is plotted between log Ct and time t at various intervals of time. A straight line is obtained, showing that the reaction is of first order. This is shown in figure 10. The slope of line is equal to slope equals to minus k divided by 2.303. From this, rate constant k can be calculated alternatively if write the equation 8 as log C naught divided by Ct equals to kt divided by 2.303. The plot of log C naught divided by Ct versus t will give a straight line with the slope k divided by 2.303 in figure 11. Calculation of rate constant when initial concentration is not known. Integrated rate equation can be used to test a first order reaction when the initial concentration of a reactant is not known. In such case, the initial concentration term A is eliminated. This is done as follows. Let the concentration of reactant at time t1 equals to A minus x1. The concentration of reactant at time t2 equals to A minus x2. The integrated rate equation can be written as k equals to 2.303 divided by t1 log A divided by A minus x1. K equals to 2.303 divided by t2 log A divided by A minus x2. Subtracting equation 9 from equation 10, we get k equals to 2.303 divided by t2 minus t1 log A minus x1 divides by A minus x2. If Ct1 and Ct2 are the concentration of reactants at time intervals T1 and T2, then equation 11 can be expressed as k equals 2.303 divided by T2 minus T1 log Ct1 divided by Ct2. if we plot of log a minus x1 divided by a minus x2 or log ct1 divided by ct2 versus t2 minus t1 gives a straight line passing through origin with slope equals to k divided by 2.303 is obtained, then reaction is of first order. Half-life period of first order reaction. Half-life of a reaction is the time required for the concentration of reactant to reduce of its half of its original value. The integrated rate equation is K T equals to 2.303 divided by K log A divided by A minus X. At T equals to T half of the reactant has reacted, X equals to A by 2. T half equals to 0.693 divided by K. The initial concentration term of A does not appear in the equation. Thus, half-life of a first-order reaction is independent of initial concentration of the reactant. Similarly, it can be shown that in the first-order reaction, the fractional life periods, i.e. T1 by 3 and T3 by 2 etc. are also independent of initial concentration of reactant. For example, time required to complete 1 by 3 of reaction will be given as. In general, the time required to complete nth fraction of the reaction will be T1 by n equals to 2.303 divided by k log 1 divided by 1 minus 1 by n. Fractional life method can be used to detect whether a given reaction is of first order or not. Unit of first order rate constant. The integrated rate equation for first order is k equals to 2.303 divided by t log a divided by a minus x. It is clear that k depends upon the ratio of two concentration term of time t. The unit of k is expressed in unit of time inverse. Time may be expressed in second, minute or hours. Accordingly, the units of k are second inverse, minute inverse or hour inverse respectively. Some examples of first order reaction. The first order reaction are broadly divided into two types: first order gas phase reaction and first order reaction taking place in solution. The gas phase reactions of first order are comparatively few. In these reactions, the progress of the reaction may be followed by measuring the volume or pressure of the gaseous reactants or products, whereas for the first order reaction taking place in solution, the concentration of reactant is measured at different interval of time. Kinetics of some common first order reaction is taken up in the following discussion. For the sake of simplicity, the examples of first order reactions have been divided into three categories. Decomposition reactions of first order. These reactions involve decomposition reactions in a gas phase or in a solution. The decomposition reactions which involves the change in number of gaseous molecules. The concentration term in equation equals to 2.303 divided by k log a divided by a minus x are replaced by pressures or volume terms. Few decomposition reaction of first order are discussed ahead. Decomposition of nitrogen pentaoxide N2O5, and next is decomposition of ammonium nitrate. Ammonium nitrate in aqueous solution decomposed at room temperature according to the following reaction. Next is decomposition of benzene diazonium chloride. Benzene diazonium chloride in its aqueous solution decomposes according to the following reactions. Next is decomposition of hydrogen peroxide. The decomposition of hydrogen peroxide taking place according to the equation. H2O2 gives H2O plus half O2. Next is thermal decomposition of isopropane. Azoisopropanes decompose on heating to form hexane and nitrogen according to the equation. It is a homogeneous gaseous reaction because all the reactants and products are in a gaseous state. Therefore, the progress of the reaction can be followed by measuring the pressure of reaction mixture at different interval of time. And next is first order reaction involving isomeric change. Isomeric conversion of N chloroacetanilide into parachloroacetanilide is an example of first order reaction. The isomerization takes place in acidic medium as follows: N chloroacetanilide in the presence of a positive to give parachloroacetanilide. The isomerization reactions occur when N-chloroacetanilide is treated with Ki solution in acidic medium. The study of kinetics of reactant is based upon the fact that only N-chloroacetanilide reacts with Ki in acidic medium to liberate iodine, whereas para-chloroacetanilide does not liberate into iodine. N-chloroacetanilide reacts as follows: 2Ki plus H2SO4 gives K2SO4 plus 2Hi. A known volume of reaction mixture is withdrawn at different intervals and the iodine liberated is measured by titration against a standard solution of sodium thiosulfate using stars as indicator. Pseudo-order reactions. These reactions, which are not unimolecular yet, they get obey first order equations. Some examples of such reactions are first hydrolysis of ethyl acetate and next is inversion of cane sugar. In this reaction, there are more than one reactant, but the rate of reaction depends on the concentration of only one of the reactant. Consider a general reactions. A plus B gives products. Rate equals to K, A and B. The molecularity of reaction is 2, so it is bimolecular reaction. However, when one of the reactant is present in large excess, then its concentration remains practically constant during the reaction. Suppose the reactant B is present in excess and its concentration remains practically unchanged. Under such conditions, we may write rate equals to K naught equals to K of B. Thus, the reaction appears to be second order but follows first order kinetics. Thus, the reaction which appear to be higher order but actually follow first order kinetics are pseudo first order reaction. Consider the hydrolysis of ethyl acetate. The molecularity of the reaction is 2, so it is bimolecular reaction. The concentration of ethyl acetate changes during the reaction while water is present in high concentration and thus its concentration remains practically constant. Therefore, the rate of reaction depends only upon the concentration of ethyl acetate and hence it is first order reactions. Rate directly proportional to CS3, COCO, C2H5. Thus, the reaction appears to be second order but follows the first order kinetic. Thus, the reaction which appears to be of higher order but actually follows first order kinetics are pseudo first order reactions. Kinetics of second order reactions. A reaction is said to be second order if its states depend upon two concentration terms which may be or may not be same. Therefore, there are two types of second order reactions: reactions involving only one type of reactant, involving two different type of reactants. First is rate equation for reactions involving only one type of reactant. Consider a general second order reaction. 2A gives products. Let the initial concentration of A equals to A moles per liter. Decrease in concentration of A at any time t x moles per liter. Concentration of A at time t equals to A minus x moles per liter. According to the law of mass action, the rate of reaction directly proportional to A concentration from 2 dx by dt directly proportional to A minus x की power 2 equals to K A minus x की power 2, where K is the rate constant for second order reaction. Equation first is differential rate equation. Rearranging above equation, we get dx divided by A minus x की power 2 equals to K dt. Integrating both sides, we get 1 by A minus x equal to kt plus I, where I is constant of integration. At the start of reaction, T0 and x equals to 0 because the reactant has not reacted. Substituting these values in equation 2, we get 1 by A equals to I. Putting the value of I in equation 2, we get k equals to 1 by t x divided by a into a minus x. Equation third may also be written as an alternate form. K equals to 1 by t bracket 1 by c of t minus 1 by c naught. This is a useful form of second order rate equation as we can directly calculate the concentration of reacting species at any time if the initial concentration and rate constant are known. Rate equation for reactions involving two different reactants. Consider a general second order reaction. A plus B gives product. Two possibilities can arise when both reactants A and B have same initial concentration, say A moles per liter, and the rate equation will be same as equation third. However, when the initial concentration of A and B are different at the rate equation is obtained as follows. Suppose the initial concentration of A equals to A moles per liter. The initial concentration of B equals to B moles per liter at any time T. X moles per liter of A and X moles per liter of B react to form the product. Then concentration of A at time t equals to A minus X moles per liter. Concentration of B at time t equals to B minus X moles per liter. According to law of mass action, rate of reaction directly proportional to A and B. Dx by dt directly proportional to A and B. Dx upon dt equals to k into A minus x and B minus x, where k is a rate constant for second order reaction. Rearranging equation 8, we can write dx upon A minus x into B minus x equals to k dt, resolving the left hand side term into partial fractions. 1 by A minus x by into 1 by b minus x minus 1 by a minus x into dx equals to k dt. Integrating this equation, we can write 1 by a minus b sign of integration 1 by b minus x minus 1 by a minus x dx equals to integration sign k dt, and we get the result at 1 by a minus b ln a minus x divided by b minus x equals to kt plus I, where I is the constant of integration. At the start of reaction at t0 and x0, substituting these values in equation 10, we get 1 by a minus b ln a minus 0 divided by b minus 0 equals to k into 0 plus I equals to 1 by a minus b ln a by b. Putting the value of I in equation 10, we get k equals to 2.303 t into a minus b log b into a minus x divided by a into b minus x. Alternatively, equation 12 may be written in terms of concentrations directly. Let the initial concentration of A equals to C naught A. The concentration of A at time t, similarly Ct A. The initial concentration of B is equal to C naught B. The concentration of B at time t, Ctb. Substituting A equals to C naught A minus x equal to Cta, B equal to C naught B minus x equal to Ctb in equation 12. So we get that k equal to 2.303 divided by t into C naught A minus C naught B log C naught B into C of Ta divided by C naught A into Ctb. Equation 13 gets modified if one of the reactant is present in excess. Suppose reactant A is present in excess, then A will be very large as compared to B, so that substituting values of A minus B and A minus x in equation 12, we get k equals to 2.303 divided by Ta log B A divided by A into B minus x. So we get that k into A equals to 2.303 divided by T log B by B minus x. As A is taken in excess, therefore it remains almost constant. Therefore equation 14 can be written as k dash equals to 2.303 divided by T log B by B minus x. K dash equals to k into A equals to constant. Equation 15 is an equation of rate constant for the first order reaction. The bimolecular reaction in which one of the reactant is taken in excess are called Pseudo-unimolecular reactions. These reactions follow first-order kinetics. Important characteristics of second-order reactions. A second-order reaction must obey any of following rate equations. K equals to 1 by T into X divided by A into A minus X, and K equals to 2.303 divided by T into C naught A minus C naught B into log C naught B into CTA divided by C naught A into CT of B. Second is second order reaction can be tested by following methods. First is substitution method. In this method, the values of A and B and the amount of reacting substance X at different time intervals are substituted in the rate equations, and the values of rate constant is calculated. The constancy in the value of K is indicated the second order reaction. Second is graphical method. Second order rate equation K equals to 1 by T into C 1 by C of T minus 1 by C naught may be written as K of T equals to 1 by C of T minus 1 by C naught, or 1 by C of T equals to KT plus 1 by C naught. This is an equation of straight line y equals to mx plus c. When a graph is plotted between 1 by C of T and time t at various intervals of time, a straight line is obtained, showing that the reaction is of first order. The slope of this line is equal to k, which directly gives the value of rate constant. When the reactions involve two different reactants, then equation 13 is used. Equation 13 can be rearranged as this equation is comparable to equation of straight line y equals to mx plus c, when log c of t divided by c of tb is plotted against time t. A straight line is obtained. The slope of line is, hence the value of rate constant k can be calculated. Equation 3 and 12 can also be used for calculating k by graphical method. Equation 3 can be rearranged as 1 by a minus x equals to k t plus 1 by a. Thus, a plot of 1 by a minus x must be straight line with slope equals to k. Similarly, equation 12 can be written as in the following form of log a minus x divided by b minus x equal to k into a minus b divided by 2.303 into t plus log a by b. Thus, a plot of log a minus x divided by b minus x versus time t must be a straight line having slope equal to k into a minus b divided by 2.303. Thus, the second order rate constant k can be evaluated. Third is half-life period of a second order reaction. For a simple second order reaction, 2a gives products. The rate equation is T equals to 1 by k into x divided by a minus a into a minus x, where a is the initial concentration and a minus x is the concentration at time t. Half-life t of 1 half is the time when initial concentration reduces to half. Substituting these values in above equation, we get t half directly proportional to 1 half 1 by a. Thus, the half-life period for the second order reaction is inversely proportional to the initial concentration of reactions. Similarly, it can be shown that the time required for completion of any fraction of the second order reaction is inversely proportional to initial concentration. Let us calculate the time taken for 2/3 of the reaction can be completed. That is t equals to t 2 by 3 when x equal to 2 by 3a. Substituting these values in the rate equation, first we get t 2 by 3 equals to 1 by k into 2 by 3a divided by a into a minus 2 by 3a equals to 1 by k multiplied 1 by 2a. The fractional life method can be used to test whether a given reaction is of second order or not. For this unit of second order, rate constant is equals to liter mole inverse time inverse. Thus, the unit of K for second order reactions are moles by liter inverse time inverse or liter mole inverse time inverse. Thus, if the time is expressed in second, minute, or hours, the unit of K will be liter per mole per second, liter per mole per minute, liter per mole per hour, respectively. Kinetics of third order reaction. A reaction is said to be of third order if its rate depends upon three concentration terms whose rate is same or may not be same. There are three types of third order reactions. A reaction involving three different molecules of different reactants. Second, reactions involving two different reactants. Third, reaction involving three molecules of single reactant. The constant K is called as the rate constant for third order reaction. The simplest case of third order reaction is 3A gives product. The integrated rate equation for such a reaction is derived as follows. Let the initial concentration of A equals to A moles per liter. Decrease in concentration of A at any time t equals to x moles per liter. Concentration of A at time t equals to A minus x moles per liter. Applying live mass action, the rate of reactions directly proportional to A cube dx upon dt directly proportional to A minus x cube equals to K into A minus x cube, where K is the rate constant for third order reactions. Equation 1 can be written as dx upon A minus x cube equals to K dt. Integrating this equation, we get 1 by 2 into A minus x square equals to kt plus I, where I is the constant of integration when t equals to 0 and x equals to 0. We get I equals to 1 by 2 square. Put value of I in equation 2. We get k equals to 1 by 2t into x into 2a minus x divided by a square into a minus x square. Equation third may be written as an alternate form. K equals to 1 by 2t into 1 by ct square minus 1 by c naught square. Important characteristic of third order reaction. A third order reaction must obey rate equation, third order rate. This can be tested by substitution method or graphical method. Half-life period of a reaction. Half-life period of a reaction may be defined as the time during which the concentration of reactant is reduced to half of its original value. It may also be defined as the time required for completion of half of the reaction. It generally denoted as T half. The half-life period for a reaction of zero order, first order, second order, and third order have been calculated during this earlier discussion. A brief comparison of all these is summarized as follows. A. For a zero order reaction, T half directly proportional to A. It is obvious that for a zero order reaction, the half-life period is directly proportional to the initial concentration. Second is for a first order reaction, K equals 2.303 divided by T log A divided by A minus X, or T equals to 2.303 divided by K log A divided by A minus X. At T equals to T half, X is equal to A half, T half equals to 0.693 divided by K. It is clear from this relation that for a first order reaction, the half-life period is independent of the initial concentration. For a second order reaction, T half inversely proportional to 1 by A. For a third order, T half inversely proportional to 1 by A square. That is, the half-life period for third order reaction is inversely proportional to the square of initial concentration of reactant. In general, for a reaction of nth order, the expression of half-life of time is T half inversely proportional to 1 by A raised to power n minus n 1. Molecularity of a reaction. According to collision theory, for a chemical reaction to occur, the reacting molecules must collide with each other. The number of reacting species which collide simultaneously to bring about a chemical reaction is called a molecularity of a reaction. The molecularity of a reaction can be 1, 2, or 3. In case of elementary reaction, that is the reaction which involves single step, the molecularity is simply the sum of molecules of reactants, as in the balanced chemical equation. Following are some examples of molecularity of elementary reaction. Decomposition of hydrogen peroxide. Second, dissociation of hydrogen iodide is a biomolecular reaction which, because two molecules collide to bring about the reaction, hence its molecularity is 2. Third is the reaction of nitric oxide and oxygen is a trimolecular reaction because it involves collision of three reacting molecules. In similar way, we can accept reactions which involve the collisions of four of more molecules. However, it has been observed that reaction involving three or more molecules are uncommon. The reason of this is that the chances of simultaneous collisions of three or more molecules are very small. In case of complex reaction, the balanced chemical equation involves large number of reacting species is usually more than 3. In case of complex reaction, the balanced equation involves large number of reacting species atoms, but the chances of simultaneous collision of such large number of species is very rare. Such type of reactions take place through two or more consecutive steps. In case of multi-step reaction, the slowest step is the rate determining step. Mechanism and rate law. We have learned that the complex reaction take place through a sequence of two or more consecutive steps. Each step is eliminatory step and involves the simultaneous collision of two or three species. The detailed description of various steps by which the reactants change into product is called mechanism of the reaction. The steps which contribute to the overall reaction are called eliminatory reactions. In case of multi-step reactions, each eliminatory step occurs at a different rate. Some steps are fast while other are slow. The step which occurs much more slowly than other step in the rate controlling or rate determining step in the proposed mechanism. The slow step has occurred. The other step will take place to form the product. Thus, the slow step determines the rate of the reaction. Thus, the experimentally observed expression which involves the reactant molecule on which the rate of reaction actually depends is called the rate law equation. It is illustrated by following examples. Reaction of first order. First is thermal decomposition of dinitrogen pentoxide. Second is bromination of acetone. Second is reaction of second order. First is reaction between NO2 and F2 to form NO2F. Second is decomposition of hydrogen peroxide. Third is oxidation of hydrogen bromide with oxygen. Third is reaction of third order, reduction of nitric oxide with hydrogen. Second is oxidation of hydrogen bromide by hydrogen peroxide. Next is differences between molecularity and order of reaction. Molecularity. In a simple or elementary reaction, molecularity is the number of molecules of the reactants as present in the balanced chemical equation, whereas in complex reaction it is equal to number of molecules present in the rate law equation. A molecularity is theoretical concept. Molecularity can have an integral value only that is always a whole number. Molecularity of a reaction cannot be zero. For a simple reaction, the molecularity can be obtained from stoichiometry of the chemical equation, whereas the order of reaction is the sum of the powers of the concentration terms in the rate law expression. Second, the order of reaction is determined experimentally, and order of reaction need not be a whole number, that it can have a fractional value also. Order of reaction can be zero. Order of even a simple reaction may not be equal to number of reacting molecules present in balanced chemical equation. Method for determination of order of a reaction. There are number of methods for determining the rate law of first order of reaction. The following methods are commonly used. First is use of integrated rate equation. In this method, the initial concentration of reactant and concentration of one of the product is measured by some suitable method. Then any one of these following method is used for determination of the second for the order of reaction. First is substitution method, second is graphical method. For a zero order reaction, K equals to 1 by T into C naught minus Ct. Second, for a first order reaction, K equals to 2.303 divided by T log C naught divided by C of T. For a second order reaction, K equals to 1 by T into CO 1 by C of T minus 1 by C naught. For a third order reaction, K equals to 1 by 2T into 1 by Ct square minus 1 by C naught square. Second, differential rate equation method. Wants of differential method. We have discussed that in first order reaction, the rate is proportional to one concentration term, and second order reaction, the rate depends on two concentration term, and so on. In general, the rate of reaction of nth order is proportional to the nth power of concentration. where K is the rate constant and C is the concentration at any time t and N is the order of reaction. For two different concentration, we can write R1 and R2. R1 equals to minus d of C1 divided by dt equals to K C1N, and R2 equals to minus dC2 divided by dt equals to Kc2N. Taking logarithm on both sides of above equations, we get log R1 minus log of R2 equals to n log C1 minus n log of C2, where n equals to log of R1 minus log of R2 divided by log C1 minus log C2. Thus, the order of reaction can be calculated using equation 6. The order of reaction n can be calculated with the values of rates R1 and R2 at two different concentrations C1 and C2 are known. This can be done by any of the following methods. First is the small change in the concentration. Del C of the reactant is measured in small time interval del t. The value of del C divided by del T is assumed to be constant in a given time interval. Hence, del C divided by del naught T can be taken equal to dV divided by dt. Therefore, the values of R, that is dC1 divided by dt, and R2, that is dC2 divided by dt, at two different concentrations C1 and C2 can be calculated. Second is, in this method, the rate is determined by plotting concentration of reactants against time. The slope dC1 divided by dt, that is R1, and dCT2 divided by dt, that is R2, at two different concentrations at a given time interval is measured by drawing tangents at that point. Using the values of slope R1 and R2 in equation 6, the order n can be calculated. Next is half-life period method. This method is also known as fractional change method. Half-life period of a reaction is the time during which the concentration of reactant is reduced to half of its initial concentration. We also know first half-life alpha initial concentration for a zero order reaction T half directly proportional to A. Second, half-life is independent of initial concentration for a first order reaction. Third is half-life is inversely proportional to the concentration for a second order reaction. T half directly proportional to A square for second order reaction. Half-life is inversely proportional to the square of initial concentration for a third order reaction. In general, for an nth order reaction, for two different initial concentration A1 and A2 may be right. We get, solving for n, the order of the reaction we get n equals to 1 plus log T half 1 minus log T half 2 divided by log A2 minus A1. Substituting the values of two initial concentration A1 and A2 and half-life period from two experiments, the value of n can be calculated. Fourth is Ostwald's isolation method. This method is employed in determining the order of reaction which involve two or more reactants. This method is based on the principle that the contribution of the reactant taken in excess to the order of reaction can be neglected. In this method, the concentration of all taken in excess to the order of reaction can be neglected. In this method, the concentration of all but one reactant are taken in excess. Then the concentration of those reactants taken in excess will remain almost constant, and the concentration of reactant present in small concentration is varied. The rate of reaction will vary with the concentration of the isolated reactant. This helps to predict the order of reaction with respect to one reactant. In this way, one reactant is isolated from others and observed. This process is repeated with other reactants one by one, and order with respect to each reactant is determined. The overall order is the sum of all these orders. For example, consider the general reaction. Suppose we isolate A by taking B and C in large excess and get order of reaction with respect to A. Similarly, we isolate B by taking A and C in excess and isolate C by taking A and B in excess, and obtain the order of respect B and C respectively. Overall order of reaction N equals to X plus Y plus Z. Next is effect of temperature on rate of reaction, Arrhenius equation. In 1889, Arrhenius gave the quantitative relationship between the temperature and the rate constant and hence the rate of reactions. The expression is called Arrhenius equation and is written as K equals to AE raised to power minus EA divided by RT, where A is constant called frequency factor and E of A is the energy of activation, R is the gas constant and T is the absolute temperature. The factor E raised to power E minus A divided by RT gives the fraction of molecules having energy equal to greater than activation energy. The activation energy EA represents the minimum energy that the reacting molecule must possess before undergoing a reaction. Activation energy E of A cannot be measured directly but can be calculated using Arrhenius equation as follow. And we get log K2 divided by K1 equals to E of A divided by 2.303 R into T2 minus T1 divided by T of A into T2. Thus, knowing the value of rate constant K1 and K2 at two different temperature T1 and T2, the values of activation energy EA can be calculated. Equation 5 can also be used to calculate rate constant at any temperature if the rate constant at any temperature and the value of EA is known for a particular reaction. Alternatively, the energy of activation EA can be calculated by writing the Arrhenius equation in the form of equation of a straight line. Equation 1 may be written as ln k equals to minus EA divided by RT plus ln A. 2.303 log k equals to minus EA divided by RT plus 2.303 log A. Log k equals to minus EA 2.303 RT plus log A. This equation is in the form of y equals to mx plus c. When log k is plotted against 1 by t, we get a straight line in figure 1. The intercept of line is equal to log a and the slope is equal to minus e of a divided by 2.303 r. Knowing the value of slope and gas constant r, activation energy can be calculated as e of a equals to 2.303 multiply r multiply slope.